Hi everybody, welcome to the poster session presentation from the Series Cybernetics Corporation from Germany. These are all our robots that we would have loved to bring to the competition, but I guess you all know the story and that's why we move on to the content right now. So, this is one thing I want to talk about tonight. This is the learning from demonstration, which we have been working on over a decade now. And it's a simple thing. You want to teach the robot a new ability that it has not yet, and you don't have any clue about programming. So what you can do is you can show the robot how to do something. And if you would, we take this pouring task here as a simple example. If you would just demonstrate that once, the robot would just simply learn it like a teach-in thing from an industrial robot and wouldn't understand anything about the task. So what we have to do is we have to do more than one demonstration with shifting the positions of all the objects involved. And what results then is if we look at, for instance, some trajectories corresponding the end effector distance to some involved objects, you see that there are parts in the demonstrations that have a very small and low and high variance. And the low variance parts is what we consider a constraint. And this is something that is relevant for re-executing the task and can then be used to form a generalized trajectory that is able to reproduce the task even in situations where the objects are totally differently placed as they were before. Again, without programming one single line. Now, the classic approach is here, use the joint space. So you just record all the robot's joints and then you can reproduce that stuff, and you can also form generalized trajectories without the need of an inverse kinematics planner. What we're doing now is, what we have done is we have transformed this into the task space. So we only need a 6-dimensional vector and the gripper state in order to do a demonstration. This enables us to use hand tracking frameworks and other stuff to do the demonstrations. The result is the same. So we are still having these generalized trajectories, but now we only have the end-effector positions, which enables us to use planners in between and also makes the whole demonstration part way more robot independent, because before it was really stuck to this one robot model. Now we can transfer the knowledge from one robot to another. And the next step here, which we are also working on at the moment, is to transform that into a higher level reasoning, so calling high level learning from demonstration, which starts to understand or starts to address the simple grounding problems when you're doing demonstrations like that, to enable the robot to understand what it's actually doing. Next part is something that we call situation awareness. This is dependent on a graph database world model. I'm not going to go into deep details here. I think most of you will know what this stuff is about. And what are we applying it to at the moment? So we are using this first of all to learn user habits. So each of you has its own way to organize your home. And this is what we are particularly interested in. So the robot observes how your home is organized over a longer period of time, and then forms spatial and temporal clusters with respect to everything that is there in a situation. So if, for instance, the Pringles can would be standing on your desk at 7 p.m. and there is an open beer bottle next to it, that might be something that some of you would consider as okay, and some of you would say, no, this has to be moved away. And these are the things that we are storing and learning, and with this high dimensional clustering, we are able to predict if a situation, given the circumstances, is okay or not. Another thing where we have applied this is when we are learning concepts. So in this case, this is referring to a tabletop setup experiment. So we're setting a table for dining as exercise. This is, by the way, something that we would also show in the open challenge. And the idea here is also pretty simple. The robot is presented various scenes that are labeled okay and not okay. And with that, we are training a Gaussian mixture model in order to generate actions. First of all, classify if the scene is okay or not, and also to get as action pairs out of it, what would be the corresponding set of actions in order to transform this scene back into a normal state where it would be okay. Good. These are 30 seconds left, but in this case I would call it even, and take care, stay healthy, and bye-bye.